Welcome to this problem walkthrough. Today, we'll be solving LeetCode problem number 1071, titled Greatest Common Divisor of Strings. This is an interesting problem that involves string manipulation and the concept of common divisors. Let's dive in and explore the solution step by step. The problem asks us to find the largest string, called x, that divides two given strings, str1 and str2. A string x is said to divide another string y if y can be constructed by repeatedly concatenating x one or more times. For example, the string abc divides abcap because abcap can be formed by concatenating abc twice. The input consists of two strings, str1 and str2, and the output is the greatest common divisor string of the two. If no such string exists, we return an empty string. Let's consider an example to clarify this further. Suppose str1 is abcap and str2 is abc. The output for this example would be abc. Why? The string abc is the largest string that divides both str1 and str2. Looking at str1, it can be formed by repeating abc twice, abc plus abc equals abcap. Similarly, str2 can be formed by repeating abc once, abc. Therefore, abc is the greatest common divisor of the two strings. Here's another example where str1 is ababab and str2 is abab. In this case, the output is ab. The string ab divides both str1 and str2. For str1, we can form ababab by concatenating ab three times, ab plus ab plus ab. For str2, abab can be formed by concatenating ab twice, ab plus ab. Hence, AB is the largest string that divides both. Now, consider a scenario where there's no common divisor. If str1 is leet and str2 is code, the output will be an empty string because there is no string that divides both. The input strings consist only of uppercase English letters, and their lengths are constrained between 1 and 10,000. Some important edge cases to consider include when there is no common divisor, such as when the strings have no shared prefix or structure. In that case, the result is an empty string. If one string is formed by repeatedly concatenating the other, the smaller string will be the result. For example, if str1 is xyz and str2 is xyz, the output will be xyz. If both strings are identical, the result will simply be the string itself. For instance, if both are AAA, the output is AAA. Finally, when the lengths of the strings are not multiples of each other, the function must evaluate possible prefixes. For example, with str1 as ababab and str2 as abab, the result is ab. To solve the problem of finding the greatest common divisor of two strings, we want to determine the largest string, referred to as x, that can be repeated to form both str1 and str2. Let's start by discussing the brute force approach. The intuition here is straightforward. We consider all possible divisors of one string, say str1, and check whether those divisors can also generate str2. We do this by iterating through all substrings of str1 that could potentially be divisors. For each candidate substring, we repeatedly concatenate it to check if it matches both str1 and str2. If it does, we keep track of the largest valid divisor. While this approach is conceptually simple, it has a significant drawback. The time complexity is cubic in the worst case, which arises from generating all substrings of str1 and then verifying each of them. This makes the brute force method impractical for longer strings, as its inefficiency becomes apparent with larger inputs. Now, let's look at a more efficient solution, the optimized approach using the greatest common divisor, or GCD. The key insight here is that the problem of finding a common string divisor is analogous to finding the GCD of two numbers, but in the context of strings. The first critical step is to check whether the concatenated order of the strings matches. If str1 plus str2 is not equal to str2 plus str1, we can immediately conclude that no common divisor exists, and the answer is an empty string. However, if the concatenated strings do match, the next step is to compute the GCD of the lengths of str1 and str2. This GCD value, which we'll call GCD_len, gives the length of the largest common divisor string. Finally, we return the substring of str1 that corresponds to this length. This approach is highly efficient, running in linear time relative to the shorter string, since string concatenation and the GCD computation are both fast. It also uses constant space, making it an excellent choice for this problem. By leveraging mathematical insights, we avoid the inefficiencies of brute force and achieve a scalable solution. Another alternative is the recursive approach, which also builds on the concept of GCD. Here, the intuition is to repeatedly reduce the problem size by stripping away common prefixes of the strings. If one string is a prefix of the other, we reduce it by removing the prefix and then recursively call the function on the shortened strings. The process continues until one of the strings becomes empty, at which point the other string is returned as the greatest common divisor. While this method mirrors the logic of the GCD approach, it introduces additional overhead due to recursion. Specifically, the time complexity is similar to the optimized GCD-based solution, but the space complexity increases because of the recursion stack, which can be problematic for very large inputs. Ultimately, the best choice is the optimized GCD approach. Its efficiency, simplicity, and memory usage make it superior to both the brute force and recursive methods. By recognizing the relationship between string divisors and the GCD of their lengths, we eliminate unnecessary checks and achieve the most effective solution for this problem. To tackle the problem of finding the greatest common divisor of two strings, we first need to understand the concept of divisibility in the context of strings. A string x divides another string s if s can be constructed by repeating x a certain number of times. For instance, the string ABC divides abcap because abcap is just 2 repetitions of ABC. This means that for str1 and str2 to share a common divisor string, they must share a repetitive structure, starting with a common prefix. Additionally, we can establish a basic condition: if the concatenations str1 plus str2 and str2 plus str1 don't produce the same result, then no common divisor string exists. This is because this inconsistency indicates that the strings don't align in a way that would allow any shared repeating pattern to exist. Building on this idea, we use the mathematical property of the greatest common divisor, or GCD, to find the length of the potential divisor string. If x is the greatest common divisor string of str1 and str2, its length must be the GCD of the lengths of str1 and str2. To calculate this, we first compute the lengths of the two strings, len1 and len2, and then determine their GCD, which we will call GCD_length. This GCD_length tells us the length of the potential divisor string. Once we have this length, we extract the prefix of str1 with a length equal to GCD_length as our candidate string. We then verify if this candidate string divides both str1 and str2 completely. This involves checking if str1 can be reconstructed as the candidate repeated len1/GCD_length times and if str2 can be reconstructed as the candidate repeated len2/GCD_length times. If both conditions hold true, then this candidate is the greatest common divisor string. This approach works because the GCD of the lengths of the strings ensures that any potential divisor string will fit perfectly into both strings without leaving any remainder. The concatenation condition is equally important, as it confirms that the two strings share a consistent repetitive structure, which is a necessary property for a common divisor string to exist. The algorithm primarily involves string manipulations, such as extracting substrings and testing for equality, along with integer calculations to determine string lengths and compute the GCD. Together, these steps ensure that we can efficiently identify the greatest common divisor string, if one exists. Analyzing the complexity of this algorithm, the time complexity is O, n plus m, where n and m are the lengths of str1 and str2, respectively. This includes the cost of computing the GCD using the Euclidean algorithm, which runs in O, log, min, n, m, and the checks for string concatenation and divisibility. The space complexity is O, GCD_length, as we only need to store the candidate divisor string, which has a length equal to the GCD of len1 and len2. Let's walk through an example to see this in action. Suppose str1 is abcap and str2 is abc. First, we check the concatenation condition: str1 plus str2 equals abcap, and str2 plus str1 also equals abcap, so we proceed. Next, we compute the GCD of their lengths: len1 is 6, and len2 is 3, so GCD_length is 3. This means our candidate divisor string is the first 3 characters of str1, which is ABC. Finally, we verify that ABC divides both strings completely. str1 equals ABC repeated 2 times, and str2 equals ABC repeated 1 time. Since both conditions are satisfied, the result is ABC. In this case, the string ABC is returned as the greatest common divisor because it divides both strings perfectly. Now, let's consider some edge cases. If the strings have no common divisor, such as str1 being ABC and str2 being def, the concatenation check will fail, and we immediately return an empty string. If the strings are identical, such as str1 and str2 both being quad A, the GCD of their lengths equals their length, and the entire string is returned as the divisor. Finally, if one of the strings is empty, no non-empty string can divide an empty string, so we return an empty string in this case as well. These edge cases highlight the robustness of the algorithm in handling various scenarios. This solution tackles the problem of finding the greatest common divisor, GCD, of two strings. The key insight is to consider both the mathematical concept of GCD for the lengths of the strings and the structure of the strings themselves. We start by checking if the concatenation of str1 and str2 in different orders, i.e., str1 plus str2 and str2 plus str1, produces the same result. This ensures that one string can indeed be formed by repeating the other. If the concatenated results are different, it implies no common divisor string exists, so we return an empty string. Next, we calculate the GCD of the lengths of the two strings using Python's math.gcd function. This GCD represents the length of the largest string that can divide both str1 and str2. Finally, we return the prefix of str1 that corresponds to this GCD length. This prefix is guaranteed to be the greatest common divisor string because of the initial validation step and the properties of the GCD. This approach is efficient, as it leverages the mathematical properties of GCD and avoids unnecessary string manipulations. The overall complexity is dominated by the computation of the GCD and basic string operations, making it highly performant for large inputs. In this implementation, we define a public method called GCD of strings that takes two strings, str1 and str2, as inputs. The first step checks if the concatenation of the two strings in different orders is equal. Specifically, if str1 plus str2 does not equal str2 plus str1, it means there is no common divisor string, and we immediately return an empty string. This ensures that the strings must form valid repetitions of some common substring. Next, we calculate the greatest common divisor, or GCD, of the lengths of the two strings using the helper method GCD. This GCD value represents the length of the largest substring that could divide both strings. Finally, we return the prefix of str1 with a length equal to the calculated GCD, as it represents the greatest common divisor string. The helper method GCD uses the Euclidean algorithm to compute the GCD of two integers, iteratively reducing the problem until the remainder becomes 0. Here, the main method provides an example of how to use the solution class and its GCD of strings method. We create an instance of the solution class and test the method with three different inputs. In the first example, GCD of strings is called with the strings abcab and ABC. The output is ABC, as ABC is the largest substring that can divide both strings. In the second example, the inputs ababab and abab result in the output AB, which is the greatest common divisor string. Finally, for LeetCode, the method returns an empty string because there is no common divisor string between these two inputs. These examples demonstrate how the method efficiently determines the GCD string or confirms that none exists. Here, we start with the first example where str1 is abcap and str2 is ABC. The first step is to check if the concatenation of str1 and str2 in both orders results in the same string. When we compute str1 plus str2, we get abcapcap, and when we compute str2 plus str1, we also get abcapcap. Since these are equal, we can proceed to the next step. Now, we calculate the greatest common divisor, or GCD, of the lengths of str1 and str2. The length of str1 is 6, and the length of str2 is 3. The GCD of 6 and 3 is 3. Using this GCD value, we extract the prefix of length 3 from str1. The prefix of abcap with length 3 is ABC. This gives us the final result for this example, which is ABC. Now, let's move to the second example where str1 is ababab and str2 is abab. Again, we start by checking if the concatenation of str1 and str2 in both orders is the same. When we calculate str1 plus str2, we get a babababab, and when we calculate str2 plus str1, we also get a babababab. Since these are equal, we move forward. Next, we calculate the GCD of the lengths of str1 and str2. The length of str1 is 6, and the length of str2 is 4. The GCD of 6 and 4 is 2. Using this GCD value, we extract the prefix of length 2 from str1. The prefix of ababab with length 2 is AB. So, the final output for this example is AB. Finally, in the third example, str1 is leet and str2 is code. When we check the concatenation, str1 plus str2 gives LeetCode, and str2 plus str1 gives code elite. Since these two values are not equal, we immediately return an empty string as the result. The output for this example is an empty string, represented as. To analyze the time complexity of our solution, we can break it down into individual operations. First, we perform a string concatenation check to ensure that str1 plus str2 equals str2 plus str1. In the worst case, this requires traversing both strings entirely. If n is the length of str1 and m is the length of str2, the concatenation itself takes O, n plus m, and comparing the resulting strings also takes O, n plus m. Next, we calculate the greatest common divisor, or GCD, of the lengths of the two strings. The GCD calculation uses the Euclidean algorithm, which runs in O, log, min, n, m. Finally, we extract a substring of length GCD, len, str1, len, str2, from str1. Extracting a substring of this length involves a linear operation and takes O, GCD underscore length, time, which is at most O, min, n, and m. These three steps together form the foundation of our time complexity analysis. Now, combining the complexities of all the steps, the total time complexity becomes O, n plus m, for the string concatenation and comparison, plus O, log, min, n, m, for the GCD calculation, and finally O, min, n, and m, for the substring extraction. Among these, the dominant term is O, n plus m, as the string operations take the most time. Therefore, the overall time complexity of this solution is O, n plus m. On the space complexity side, we first consider the temporary strings created during concatenation. The space required for str1 plus str2 and str2 plus str1 is O, n plus m. The GCD calculation itself operates using constant space, or O1, since it only involves arithmetic operations on integers. Lastly, extracting the substring creates a new string of length GCD underscore length, which requires O, GCD underscore length, space and is at most O, min, n, and m. Bringing these observations together, the total space complexity is dominated by the string concatenation, resulting in O, n plus m. To put this in context, let's compare the current optimized approach with a naive alternative. A brute force method would involve finding all possible prefixes of str1 and str2, checking if each prefix divides both strings, and then determining the longest valid prefix. This approach requires iterating through all prefixes and performing divisibility checks, resulting in a time complexity of O, n asterisk m in the worst case. In contrast, the optimized solution avoids explicitly checking prefixes by leveraging the Euclidean algorithm for GCD and the properties of string concatenation. This reduces the time complexity to O, n plus m, making it significantly more efficient. Finally, let's consider the best, average, and worst cases for this solution. In the best case, the two strings are identical, so the concatenation check is trivial, and the GCD calculation is minimal, leading to a time complexity of O, n plus m. In the worst case, the strings are entirely different, meaning we still perform the concatenation and comparison in O, n plus m, before returning an empty string. Even in this scenario, the complexity remains linear. On average, the solution efficiently computes the GCD and extracts the substring in O, n plus m. Mathematically, the dominant term in both time and space complexity comes from the string operations, which scale linearly with the input sizes. As a result, the overall complexity is consistently O, n plus m, making this approach robust and optimal for this problem. When solving this problem, there are some common mistakes to watch out for. First, many people assume that a greatest common divisor string must always exist. However, this is not true if the concatenation order of the strings differs. Specifically, if str1 plus str2 is not equal to str2 plus str1, there can be no common divisor. Failing to check this condition will lead to incorrect results. Another common issue is misunderstanding the difference between a substring and a divisor. Just because a substring exists within str1 or str2 doesn't mean it can be a divisor. A valid divisor must be able to fully reconstruct the original strings through repeated concatenation. Lastly, overcomplicating the solution by manually checking all potential divisors with loops is inefficient. This approach not only has poor performance but also ignores the mathematical relationship between the lengths of the two strings and their greatest common divisor. Now, let's talk about some additional mistakes that can trip you up. Ignoring edge cases is a frequent oversight. For instance, if one of the strings is empty, or if both strings are identical, failing to handle these scenarios explicitly can result in runtime errors or incorrect outputs. Another mistake involves misunderstanding how to use modulus with strings. Since strings don't support arithmetic operations directly, trying to apply a modulus operation without proper context will fail. Instead, you should use string slicing and repeated concatenation to simulate the behavior of modulus when working with strings. Being mindful of these pitfalls will help you avoid unnecessary errors. To perform well in interviews, it's important to focus on key insights and develop a clear understanding of the problem. At its core, this problem is about the mathematical GCD of the lengths of the two strings. If the GCD of the lengths is G, the largest common divisor string will be the substring str1, G, but only if it meets the divisibility condition. Recognizing this connection between number theory and string manipulation can simplify the solution significantly. For optimization, avoid brute force checks and instead rely on the properties of string concatenation and the GCD function for efficiency. Additionally, communication is crucial in interviews. Be sure to explain why you're checking the concatenation condition, namely str1 plus str2 equals str2 plus str1, as this demonstrates your understanding of the constraints and ensures you're not performing redundant computations. Finally, practicing related problems, like finding valid anagrams or the longest common prefix, can help you build the foundational skills necessary for solving this challenge. There are also alternative approaches to solving this problem, each with its own trade-offs. The brute force approach involves checking all prefixes of the smaller string to find the largest one that divides both strings completely. While simple to implement, this method is inefficient, especially for longer strings, as it has a time complexity of n squared. A more efficient solution leverages the mathematical GCD of the string lengths. By using the GCD to determine the potential divisor string and validating it, you can achieve an O(n) solution. However, this approach requires a solid understanding of the GCD function and how it applies to strings. An elegant alternative is the recursive approach, which reduces the problem size by removing common prefixes until the GCD string is found. While concise and intuitive, this method may use more memory due to the recursive call stack. Choosing the right approach depends on the specific constraints and your familiarity with these techniques. Great job! In this walkthrough, we explored how to find the greatest common divisor of two strings using a simple yet efficient approach. We highlighted the importance of combining string manipulation with mathematical concepts like GCD. Remember to keep practicing problems like this to strengthen your problem-solving skills. Thanks for tuning in, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!